Okay, in this lecture we want to talk about the elementary matrices. So these are square matrices that correspond with the elementary row operations. So let's remember what those are. So remember there are three elementary row operations. So these are the three things that you can do to a system and not change the solution set. So if you've got a system of equations, you can always interchange two equations. Right, or like you can always interchange two rows in a matrix when you're on your way to writing it in row echelon form. You can always multiply a row by a non-zero scalar and that won't change the solution set. So you can multiply an equation by a non-zero scalar on both sides and it won't change the solution set. And then you can add a multiple of one row to another row and then replace that row with the result. So if you do this thing to a system of equations, you will not change the solution set. So remember, three elementary row operations. You can do this to a matrix, or you can do it to a system of linear equations and not change the solution set. All right, so the fundamental definition for this lecture. So a square matrix, this is really important. Otherwise, we can't talk about elementary matrix. So a square matrix, call it capital A, and it's an n by n matrix. We'll call this thing an elementary matrix if it is obtained from the identity matrix of order n by applying exactly one row operation to this thing. So here's the identity matrix of size 3. So this is the 3 by 3 identity matrix. One example of an elementary matrix is to interchange rows 1 and 3. So remember, we can interchange rows 1 and 3. So we will do that to the identity matrix. Sorry, this is 0 and 1. We will interchange the rows 1 and 3 of the identity matrix. So here's row 3. Here's row 1, and we didn't do anything to row 2. So this is an example of a 3 by 3 elementary matrix, and what does it do? It interchanges row 1 and row 3. We'll see this in an example in a bit. So here's another elementary matrix. What does it do? So we're going to take 1/2 of row 2 and replace row 2 with that new result. So instead of writing 0, 1, 0, I just write 0, 1/2, 0. So this is another example of an elementary matrix because I applied exactly one row operation to I3 and I got this thing, call it E2. And then finally, applying the row operation, multiply row 1 by -3, add that new row to row 3 and replace row 3 with that new thing. So here's the elementary row operation in symbols. So we're going to add -3 times row 1 to row 3. So take row 1, multiply by -3, and then add it to this thing. So row 1 stays the same, row 2 stays the same, but now row 3 is -3 plus 0, so you get -3. -3 times 0 plus 0 is 0, and then -3 times 0 plus 1 is just 1. So here are three examples of an elementary matrix. Each one of these represents one of the fundamental row operations. So now let's see what multiplying by these particular elementary matrices will do to a standard 3 by 3 matrix. All right, so this example should show us why we call these things elementary matrices, because when you multiply on the left, so here's any old 3 by 3 matrix. If I multiply on the left by one of these elementary matrices, it will do the same action to the rows that we did to the identity matrix. So remember, what was E1? It was the action, interchange rows 1 and 3. So when I take this elementary matrix that interchanged rows 1 and 3 of the identity matrix and multiply it by any old matrix with 3 rows, I mean, you could do this with any number of columns, right? As long as it's got 3 rows. So when I take this thing and multiply, what should it do? Well, it should interchange rows 1 and 3, right? So it carries out an elementary row operation. And what is that row operation? It's the same one that we did to the identity matrix in order to get this elementary matrix. So when I multiply this thing by this, any typical 3 by 3 or any old 3 by whatever, 3 by however many columns, it's going to interchange the rows. So row 1, twist, multiply, so I get 0, 0, and 1. So multiply, you just get G, and add everything up, you just get G. Twist, multiply, 0, 0, 1, so you just get H. Twist, multiply, 0, 0, 1, so you just get I. And then do the same thing, so when you twist, multiply, you will just get this row back, D, E, F. And then here, when I twist, multiply, and add, I just get A, 1, 0, 0, so I'm just left with A. And then here I get twist, multiply, I get B, 0, 0, B, and then same thing here, I get C. So the elementary matrix obtained from interchanging rows 1 and 3 of the identity matrix, that thing will interchange rows 1 and 3 of any old matrix with 3 rows. Doesn't matter how many columns. We could have done this, same thing, right? So this still will interchange rows 1 and 3. If there were 4 columns, it would still interchange rows 1 and 3. Doesn't matter. What is E2? Well, E2 we got by multiplying the identity matrix row by 1/2, or any non-zero scalar, it doesn't matter. So when I multiply the row I3 by 1/2, that's the same thing as multiplying our typical matrix by the second row of that thing by 1/2. So here's that elementary matrix, and what do I get when I multiply by this 3 by 3? Well, I multiply the second row by 1/2 because that's what I did to the identity matrix in order to get this elementary matrix. So go through, carry out this multiplication, and see that this is what you get. Again, scalar multiplying any row by a non-zero scalar, if you do that to the identity matrix, the resulting elementary matrix will do that same action to the corresponding row of a typical matrix. And how did we get E3? We took -3 times row 1 of the identity matrix and added it to row 3 of the identity matrix and got this new row. So this elementary matrix, when I multiply it by any old matrix with 3 rows, should do the same thing. It should take 3 times the first row, add it to the third row, and then replace the third row with that new result. So if you take this first row, twist, multiply, you will just get the same row across A, B, C. And then you can see here, we got a 1 and all zeros. That's going to leave the second row untouched. But here's where the action is, right? If I twist and multiply, it's -3 times A, 0 times D, and 1 times G, and then add all that up. So I get -3A plus G. Do the same thing to the second column. I get -3B plus H. Do the same thing to the third column. I get -3C plus I. So you can see, what action does this have on any matrix with 3 rows? Well, because I added 3 times the first row of the identity to the third row of the identity and swapped out the result, that's the exact action multiplication on the left by this thing will do. It will take 3 times row, or -3 times row 1, add it to row 3, and swap out row 3 with that new result. So the reason we call these things elementary matrices is because they correspond to elementary row operations.